In class, we discussed Chapter 1.6, Additional Equation Types. We discussed some polynomials, rational equations, radical and quadratic types of equations. So our first objective is to solve a third-degree polynomial. So there are two methods dealing with polynomials. One is factoring by grouping, and the other is a long division method. If we have even terms, and in this case we have 4, we're going to try the grouping method. If we have an odd number of terms, typically we can't group and we have to use the long division method. So the first idea for any polynomial, we're going to use the zero principle in that we're going to move all the variables and numbers over to one side of the equation. In this case, we're going to move them to the left side. So we have 12x cubed plus 24x squared minus 3x minus 6 equals 0. Now we're going to group the first two terms, which is 12x cubed plus 24x squared, and we're going to take out a 3 of the last two terms and group that. So it's a minus 3 parentheses x plus 2, and that's all equals 0. Now we're going to factor again. We're going to take out a 12 x squared from the first term, and when we do that we end up with an x plus 2, and then we leave the second term alone, which is 3 parentheses x plus 2. And so in this case we now move down to the factoring portion. We can take out a x plus 2 from both terms, and you can see that we're left with a 12x squared minus 3 times x plus 2 is equal to 0. We can take a 3 out of the first factor. When we do that, we get 3 times parentheses 4x squared minus 1 times x plus 2. And then we're going to divide 3 from both sides of the equation. When we do that, we end up with this last equation, 4x squared minus 1 parentheses x plus 2, which equals 0. You'll notice that this is a perfect factor, or perfect square, and so we can factor further. So we get 2x plus 1 times 2x minus 1 times x plus 2 is equal to 0. And when we set each one of those factors to 0, we get x is equal to a negative 1/2, x is equal to 1/2, and x is equal to a negative 2. So that's our solution for this particular third-degree polynomial. Our second objective is to look at some complex rational equations. And you will recall that the way that we're going to solve the complex rationals is to find a common denominator. That's our first step. And our second step is to multiply both sides by the common denominator. Now sometimes we have to factor to find the common denominator. So in this step we notice that this is going to be c minus 5 times c plus 1. So that's the factor for c squared minus 4c minus 5. So we're going to multiply through by the common denominator, and when we do that we get 4c times c plus 1 minus c minus 5 is equal to 3c squared plus 3. Notice that when we multiply by the common denominator, we remove the fractions for the equation. This is not like an expression where we have to adjust the expression to the common denominator. When we have an equation, we can actually multiply through by the common denominator to get rid of the fraction. And so for each of the terms, whatever's missing from the denominator, we just multiply the numerator by. So our second step from there is to go through and do the distributive property. So we get 4c squared plus 4c minus c plus 5 is equal to 3c squared plus 3. And now we're going to combine like terms, right? CLT. So we have on the left-hand side 4c squared plus 3c plus 5 is equal to 3c squared plus 3. Now again, we're going to use the zero principle, right? Since we have a quadratic or any polynomial, we use the zero principle. So we're going to move everything over to the left side of the equation. So we get c squared plus 3c plus 2 is equal to 0, and then we factor. And in this particular case, our factors are c plus 2, c plus 1. And when we set those factors to 0, we get c is equal to a minus 2, c is equal to a minus 1. But c minus 1 doesn't work because when we plug it into the equation, the original equation, we see that 1 over c plus 1 wouldn't work when c is minus 1. We would be dividing by 0. So there's only one solution here. The solution is a minus 2. The third objective is to solve radical equations, and we're only going to look at one radical equation in this particular problem. This is number 33 on page 167 of your book. So the idea is to isolate the square root on one side of the equation. We'll always isolate a square root first on one side of the equation. And then we're going to square both sides of the equation. So in this case, we isolate the square root of m plus 18, and we move the 2 over to the right hand side, so we subtract it from both sides of the equation. So we get m minus 2. Now we're going to square both sides, so we get m plus 18 is equal to m minus 2 squared. We FOIL the right side of the equation, and when we do that, we get m plus 18 is equal to m squared minus 4m plus 4. And now we use the zero principle. So now we're moving everything over to the right side of the equation. We get m squared minus 5m minus 14. You may ask, well, why on the right side on this time and the other time it was left side? We want always a positive m square coefficient. So we usually move it to the side where the square of the variable is going to be positive. It's just easier to work with. So now 0 can be factored, so we factor. And it's factorable from m minus 7 times m plus 2. And we see that we get the roots, m equals 7 and m equals minus 2 are our roots. But m equal minus 2 does not work. It's extraneous. Why? When we plug it in, we get a 6 on one side of the equation, and we get 6 is equal to a minus 2. Well, actually, we know that 6 does not equal a minus 2, so that's what makes it extraneous. So the only solution here is m is equal to 7. Here we have a little bit more complication. Here we have two radicals in an equation. This is number 42 on page 167. So we want to solve a two-radical equation. So in this particular case, we have the square root of k minus 2 equals the square root of 2k plus 3 minus 2. Had both radicals been on the same side of the equation, we would have moved one of the radical symbols over onto the other side. The reason is we want to isolate one of the radical symbols. Well, the next step, of course, is to square both sides. So from here to here, we're going to square. And when we do that, we get k minus 2 is equal to the square of the square root of 2k plus 3 minus 2. Well, we're going to FOIL the right side of the equation, right? We're going to expand it. So we're going to leave the left side alone. It's k minus 2. But when we FOIL, we get the square of the square root of 2k plus 3 minus 2 times the square root of 2k plus 3 minus 2 times the square root of 2k plus 3 plus 4. So now we want to combine like terms, and we will spend a little bit of time doing that. So the left side we're going to leave alone. K minus 2 is equal to 2k plus 3 minus 4 times the square root of 2k plus 3 plus 4. Now, in this case, we want to combine again, and we are combining the 4 and the 3 to get 7. So now we want to isolate the radical symbol again on one side of the equation. To do that, we have to move the 2k and the 7 to the left side of the equation. To do that, we subtract 2k from both sides, and we subtract 7 from both sides. So when we do that, we get a minus k minus 9 is equal to a negative 4 square root of 2k plus 3. Now we divide through by a negative, or we multiply through by a negative 1. And when we do that, we get k plus 9 is equal to 4 square root of 2k plus 3. Now again, we're going to square both sides, right? Why? Well, we still have a radical symbol over here. So when we square, we get k plus 9 squared is equal to 16 times 2k plus 3. Now we're going to expand the left side of the equation, and when we do that, we get k squared plus 18k plus 81 is equal to 32k plus 48. And now we're going to use the zero principle. So we get k squared minus 14k plus 33, and we can factor here. And we get k minus 11 times k minus 3 equals 0. And so now k is equal to 11, or k is equal to 3. It turns out that both solutions work. So that is a more complicated problem, but it's doable. Our last objective that we're going to look at in this particular chapter is solving quadratic types of equations. And the principle here is when we see a type of equation that looks kind of quadratic, we are going to use the method of substitution to make a quadratic equation. So our initial equation is 3d to the 2/3 power minus d to the 1/3 power minus 4 is equal to 0. We're going to let x equal d to the 1/3 power. When we do that, we put the substitution in for d to the 1/3, and we get 3x squared minus x minus 4 is equal to 0. Now that's factorable, and so we make our lives easy. We get 3x minus 4 times x plus 1. And so for x now, we get the roots x equals 3/4 and x equals minus 1. But this is not d. We're solving for d. So now we have to substitute back in for d to the 1/3. So we come up here and we see that d to the 1/3 is equal to 4/3. And now we cube both sides of the equation. When we do that, we get d is equal to 4/3 cubed, which is 64 over 27. So that's one of our solutions. The next solution is d to the 1/3 is equal to a minus 1. Well, when I cube both sides of the equation, I get d is equal to a negative 1 cubed, which is just negative 1. So in this case, both solutions work, and so we have the solution 64 over 27 and a minus 1. I also want you to look on page 167 of your book, and I want you to try to do problems 57 and 58. That will also help you to look at doing methods of substitution. That concludes our in-class discussion for chapter 1.6.